So here we go with the restaking panel. I'll do a quick self-introduction, and then we will let everyone introduce themselves and their projects, and then we will get into it. Right? So hello, guys. This is Michael, one of the co-founders at Blockless. What we do is we help people launch off-chain networks, trustless off-chain networks, so that their on-chain applications can become more functionally rich. Right? Nowadays, we call this off-chain networks sometimes AVSs. Right? So we're active in the EigenLayer ecosystem as well.
Okay. A very good morning. My name is Zheng. I'm the co-founder of Automata Network. So at Automata Network, we actually run a multi-prover AVS on EigenLayer. So what do? We kind of like provide TEE multi-provers for projects such as rollups or co-processors, projects that seek to kind of like diversify their prover systems, have alternate kind of like finalization mechanisms. So yeah, very glad to be here on the panel.
Good morning, everyone. My name is Ismael. I'm one of the co-founders of Lagrange Labs. Lagrange focuses on building a ZK coprocessor and a proving network. So what is a ZK coprocessor? A lot of people have been talking recently about these all over Twitter, and there's a lot of great articles. So a ZK coprocessor can simply be thought of as a scalability solution for smart contracts. Rather than scaling compute through making faster L1s or horizontally scaling L2s, you can take existing smart contracts and you can use verifiable zero-knowledge off-chain compute to prove types of computation that would otherwise be too heavy to do in that contract. Therein, you can scale the things you can do in your smart contract using mathematics, zero-knowledge proofs on the blockchains and the smart contracts that you already have deployed in production today. So we're deployed in production on EigenLayer. We support 4 chains right now, and we've been, a very happy player and a very happy participant in the EigenLayer ecosystem for quite a while.
Hey guys, my name's Yorke. I lead protocol development at Hyperlane, which is an interoperability protocol. Hyperlane's been in production for a couple years now, but with the launch of EigenLayer and Symbiotic and some of these other restaking protocols, we are layering economic security on top of our interoperability solution. And yeah, before Hyperlane, I briefly worked at Gauntlet on Era Finance, which was a treasury management protocol. And before that was at Cello doing stablecoins.
Cool. Hey, everyone. I'm Nikhil, co-founder and CEO of Aethos. Aethos is a programmable policy layer. And so what that means is we enable pre-transaction rules and conditions for any applications that are on-chain, for their smart contracts, their solver networks, their sequencer. So those pre-transaction rules and conditions help you basically, as a developer, determine what types of assets or transactions can go through. So different use cases can be for risk management, for AML, for rehypothecation and recollateralization, stablecoin minting, a number of different use cases. Think of us as the ability of doing some form of off-chain compute that's done before a transaction actually happens. Before this, I was head of strategy and innovation at Cello, so know Yorke from over there, and then have also been pretty active in the digital asset policy space.
So yeah, now we went through what each of you are doing, but we haven't actually talked about how exactly your system makes use of restaking, right? How about we go this way, and so we can talk about, okay, which part of the system is actually using restaking and how is it working?
Okay, so with the Automata kind of like multi-provers, we enforce most of our security actually through the guarantees that is given by the trusted execution environment. So a little primer, if there are people, just let me take a kind of like quick take. Like in the audience, are people familiar with TEEs? Okay, I'll give a kind of like brief overview. So TEEs are kind of like a black box. You can put code, you can put data into this black box, and the black box would do exactly what the code tasked it to do. So with this, we kind of like can get certain guarantees from this black box, namely confidentiality and integrity of the computations that are being done. So kind of like what we use TEEs for is to kind of like have an alternate computation framework or paradigm for existing zero knowledge or zero knowledge coprocessors or any coprocessors in general. So let's take a typical ZK rollup for example, right? There's some computation that is done, let's say on the L2, and then the corresponding proof for those transactions or computations are being generated. The proof would then be rolled up to the L1, committed to the L1, and if the proof verification goes through, then the L1 will actually perform the state transition from the old state root to the new state root. In this process, because ZK is actually a validity proof, if it checks out OK on the L1, it is finalized. What it means is that if there's anything wrong with the ZK circuit, be it like it's under constraint, or there's anything wrong with the verifier, then you actually might have the issue of having an invalid proof being accepted on the L1 chain. And then as a result, bad things can happen. So really what we are proposing is if something is important, then relying on one single kind of like thing to secure it, it's not a very good idea. Like the more the merrier. That's why we have client diversity in Ethereum. So with all that said, if the security is backed by TEs, why do we need the kind of like crypto economic security given by restaking, by the stake? Well, if we think about it, TEs, they actually protect. It gives confidentiality, it gives integrity, but it doesn't give you availability. So in order for us to ensure availability of the service, there's a need to disincentivize the participants, the operators, from actually being offline. So we want them to be online and providing the service. And right at the end of the day, like no matter how much guarantees we give, it's based on certain assumptions. If the assumptions are broken, then bad things can happen. So this crypto economic security will act as a form of insurance that will actually compensate the clients of the protocol in the case that something bad happens. So this is how we make use of the crypto economic security.
Thank you. Lagrange believes that the future of scaling blockchains is through zero-knowledge compute, through verifiable computation over blockchain state. And while this computation and the proofs of it can scale the types of information a smart contract can access, we can't, with simply zero-knowledge proofs, guarantee the liveness of that computation being delivered to a contract. When thinking of any decentralized system, you have to think, what is the safety of the underlying computation I'm using, the collateral, the economic security behind consensus typically, and then what is the liveness? What is the SLA over when I request something, will that be delivered back when it needs to be? And so this is where Lagrange and our zero-knowledge systems intersect with EigenLayer, restaking, and the AVS ecosystem. It is how we develop networks that instantiate provers and can guarantee that when proofs are requested from our end users, from the DeFi protocols, the NFT projects that we work with, they can be delivered back such that the computation can be leveraged within these applications. To make a very concrete example, if you have a lending protocol that's pricing some collateral based on a VWAP on a series of Curve and Uniswap pools, you need to guarantee that when a user deposits some asset, and you need to price that in order to be able to allow them to take a loan against it, that the information that you're using to price it is timely, correct, and can't be censored. And this is where we can take a zero-knowledge system that can prove this computation, and we can deploy this as a network, such that when a smart contract on Ethereum requests to this network, hey, I would like a proof of some computation, the network is able to deliver it back. And this network, at its core, uses restaking. It uses economic security to underlie every single protocol participant, such that the proofs that are delivered back have penalties if the parties computing them don't compute them on time. And so this is where Lagrange's prover network intersects with restaking. The simplest way to think of it is proofs give safety. Instantiation of your prover as a network with economic security gives liveness.
Cool. So yeah, I guess just to start with an overview of Hyperlane, it's an interoperability protocol. I think everyone's probably familiar with interoperability in the context of rollups. A rollup has a native bridge, which settles to Ethereum L1, and this is a form of interop between two networks, the L2 and the L1. And Hyperlane is what we call it a modular interoperability protocol, which basically means we enable interoperability between any two networks, irrespective of the topology of the kind of underlying chains. So we've been in production across both the Ethereum ecosystem as well as the Cosmos and Solana ecosystems. And kind of part of this modularity is enabling interoperability amongst the kind of large DeFi ecosystem that we have on Ethereum with the kind of emerging long tail of new VMs and new chains, which are maybe more experimental in terms of either the VM or consensus that they're using, which maybe don't have as kind of functional or reliable of a light client specification, which might enable us to do kind of fully trustless interoperability. And even with Ethereum mainnet's kind of consensus model, we don't have a great light client, which means we can't easily prove on other chains what has been finalized on the Ethereum main network, or at least we can't do so in a time frame which would be conducive to a consumer-grade experience, like a point-of-sale type experience. And so probably this week, you guys have been hearing all about pre-confs, which is kind of a solution to some of this. And in Hyperlane, our AVS also functions as a sort of pre-conf. And so rather than waiting for kind of finality of the origin chain, as defined by the light client spec or lack thereof, we can basically recruit validators to attest to basically a commitment to messages that are being passed between chains that is stored in the origin chain, on the origin chain in smart contracts. So they're basically just attesting to this storage root. You can think of it as that commits to all outbound messages or all outbound token bridges. And on the destination chain, without any economic security, we can accumulate kind of reputational security. So if, let's say, we have 100 reliable validators who are producing this attestation from any origin chain, we can basically just have a smart contract that's verifying threshold signatures from that validator set on the destination chain. And that looks like a reputational security model. And for pairs of chains where there isn't a great light client or there isn't a great native bridge, this has been our solution historically, is to recruit kind of reputable validators. But with restaking, and so I guess the path towards making that less trusted in terms of the set that's being curated is to add proof of stake, which is to add penalties to validators if they lie about the state attestation. And we can do that on every origin chain. And we have kind of taken some steps in that direction where we basically have a pool of stake on every origin chain that's securing outbound messages economically. But the challenge becomes basically the cost of capital of that type of architecture, where you need to recruit a separate pool of stake on every chain. And so with EigenLayer and with Symbiotic, we lower the marginal cost of capital for recruiting that pool of stake. And within the rollup ecosystem, because we have strong settlement to the Ethereum mainnet chain, we can basically use a single pool of stake on Ethereum mainnet to economically secure basically interop between any chain that has a strong settlement mechanism to Ethereum, and thereby, basically introducing fast interop. It's kind of complicated to explain. I wish I had a diagram, but I can talk to people after if they're curious to learn more.
So for us, what we're doing at the end of the day for Aethos is we have a network of operators that issues signatures if a transaction adheres to a policy. So to make that more concrete, let's take a privacy protocol that's worried about assets coming in either from an exploit or from sanctioned entities, and they're saying, hey, look, like we legally or for whatever reason don't want certain assets to come in because we don't want to become seen as a tornado cache. So that's a tangible example. So in that case, what Aethos does is that application sets that policy of they don't want certain assets. And our operator network says, hey, we're going to issue signatures if a transaction that's coming in adheres to the policy you guys have set. Great, those assets can go through. If not, those assets shouldn't go through. So in that case, we have these operators that function like a notary. The risk there is that if the operators decide to behave maliciously, let's say they don't issue signatures when they should be, or they issue signatures when they shouldn't be, they're able to basically prevent transactions from even going into the system whatsoever. And that's a concern, right? Because an operator, if they behave maliciously, basically can block transactions from even happening for that application. So where we use EigenLayer is ensuring that operators don't behave maliciously, so they have economic security. If an operator behaves maliciously, their economic security is essentially slashed. If they don't maintain uptime as well, that is something that's slashed because they, again, sit between a user and an application. So given that critical dependency that we end up sitting in between, you want to make sure there's some mechanism to ensure that operators have to issue signatures. And in our case, the signature issuance itself is deterministic. So it's set by the actual policy. The rule is set by the application themselves. So all you need is a decentralized mechanism of enforcing that in a trust minimized and open and verifiable manner. So that's why we're using EigenLayer, and that's how we use it.
So this panel is called Managing AVS Risks, and all of us builders here on the stage are operating in the off-chain space, right? And previously, before EigenLayer, everyone building in the off-chain space, right, they either do not have a token, right? Say that BitTorrent was functioning fine without a token initially, or they're issuing their own tokens, right? But now with restaking, obviously we have the slight division or this minor difference between staking and restaking, right? So for you guys, how do you guys perceive as the difference between native staking and restaking? What are the different risk factors involved? And why did you guys end up choosing restaking?
Coming at the hard questions. I can kick this one off. So one of the most powerful and often overlooked functions that restaking gives you is cheap cost of capital. I think a lot of people in crypto who haven't been involved necessarily in developing a protocol don't understand how damaging high cost of capital coupled with high emissions can be to a protocol's longevity. What restaking offers is usually 1 to 2 orders of magnitude cheaper capital in the form of restaked ETH or restaked ETH equivalent than what you would get from native staking. And so with this, you have more price security, since ETH is obviously more stable than a lot of these native assets. It's much cheaper, and it's much more abundant, and it's much easier to convince people to just stake their ETH with you than buy your token, accept the risk of your token going down in price, and then having to receive more of your token as an emission. And so concurrently with this point of this being a much more advantageous structure for stake, the flip side is you do face some risks. And one of the principal risks you face is if the pool of capital that you rely on is slashed, if it's pooled security by another actor, you may not have at a point in time the amount of security you would anticipate. And this is why great protocols like EigenLayer have programmatic constraints, things like StakeSure, things like attributable security, that allow the protocols developing on top of them to have higher degrees of certainty that in the event they need to have a certain amount of slashable economic security at any point in time, they can have that with the underlying protocol designs that they build on.
Yeah, I can add a little bit to that. So I think, yeah, by leveraging restaking and this kind of more efficient capital allocation, you are basically taking on all the exogenous incentives of your operators into whatever AVSs they're kind of opting into. And there may be times where kind of the profit from corruption in your protocol or in your AVS is low, but in some other AVS it's high, and so someone might be willing to commit fraud in your in the context of your AVS slashing conditions if the kind of payoff function across all the AVSs that they're opted into is large enough. And so, yeah, there's basically this fundamental trade-off between the capital efficiency of the stake and kind of how leveraged it is, or how restaked it is across many different AVSs, and kind of the larger the set of AVSs, the kind of lower cost of capital, but the kind of higher exogenous risk of the operator set, and kind of their incentives. And yeah, I think just in terms of, to draw an analogy, I guess, to the Cosmos ecosystem, people often point to kind of one of the reasons for why the Cosmos ecosystem has maybe, some might say has failed to, I guess, reach the mainstream, is this kind of competitive dynamic between these different pools of stake that are forming these ecosystems that, the ecosystem was built to be kind of natively interoperable, but there's kind of these parasitic and competitive incentives between different chains' security budgets. And on the flip side, in the Ethereum ecosystem, we have these rollups who are all kind of sharing a security budget in the form of Ethereum DA. And you can get potentially more cooperative incentives. And so I think even though there are these kind of exogenous risks for AVSs, in many cases you can have cooperation amongst these protocols that are leveraging a proof of stake and slashing system rather than kind of this competitive dynamic.
Adding to that as well is that, so when you think of economic security and you're integrating with different applications, they're essentially trusting you to some extent, right? That you don't go down. And if you're using your own native token, their now trust assumption is in your own token, that your token holds value in the long term, that for whatever they're doing, there's now exposure to your token as a result of that. And so in the case of something like restaking, you're actually able to say, look, the trust assumption is less so on our token to start. It's actually on you can look at it from an Ethereum standpoint, the value of ETH. So that's quite powerful if you're actually trying to bootstrap use cases. So I think the cost of capital is a particularly important point. I think that was like one of our biggest considerations, to bootstrap economic security, because alternatively you either have to launch a token, have sufficient value in your token to guarantee economic security for a sustained period of time, or you have to create a proof of authority model, right? That was the other thing we looked at, was we can use the proof of authority model and say we have a trusted set of operators on day one. Using restaking, you're able to avoid that. That being said, there are considerations here though, right? Because now you're thinking about, you're using a restaked asset. And so then it's okay, great. So if you're using some form of restaked asset and you're using an LRT, what are the trust assumptions you might have for that? And that's, I think I think, Michael, those are some of the questions you had, but that's an important consideration, because now if there's a depeg of that LRT, what are the implications that it has for your economic security? So you have to understand that really well. You have to be really particular around how you think about the makeup of your LRTs from an economic security standpoint.
So I guess other than having additional risk from counterparties, because now we have to rely on, say, restake token project, right? But other than those, I think one of the things that we have to be aware of, yes, capital is cheaper, but the security is actually pooled. So in the case where something happens, how is this security actually being slashed and distributed to the different AVSs? Or like, for example, if an operator staked, if an operator participates in, say, 20 different AVSs and misbehave in one of them, how is the distribution going to happen? How is the slashing going to happen? Well, in the white paper, it seems like it will be distributed equally among all the AVSs, because what's it called? Because of race conditions that can actually happen and attacks that can be formed. But so when we are kind of like designing an AVS, then we will actually have to be a little bit more careful on like the actual amount of security or insurance that each of the AVS actually have. Yeah.
I see. So I guess fast forward a little bit, right, as we're talking about sloshing risks and so on. When you guys are designing your AVS, right, what are the tactics or that you guys are using to really, I mean, obviously we're using the stake for something, right, but we also want to avoid sloshing, right? We're incentivizing the node operators for doing this set of things, but you know, in normal conditions, we don't want to punish them, right? Because at the end, stakers will be punished. Yeah. So, what might be some of the strategies or mechanisms that you have implemented, right, to avoid sloshing on this front?
Yeah. So I want to start, since it's early in the morning, and I hope everyone here can wake up a little bit, with a somewhat contentious statement. Not every POS system needs slashing, and not every AVS should use slashing. I think that there is a lot of excitement and a lot of fear over what happens when slashing gets added to the restaking protocols in the space. But it's important to understand that if we look at production POS systems, Solana doesn't have slashing, Avalanche doesn't have slashing. So in reality, you can have these production-grade POS systems that don't, in fact, require slashing. And why is this? Well, because large pools of capital have an implicit cost of capital. And to sanction against the rewards of an operator within these protocols is an economic penalty in and of itself without compromising the principle. And to put this in a very concrete way, say you have $1 billion staked and the risk-free rate is 2%, so you anticipate 20 million in rewards on that per year. I say, you missed a slot proposing a block, so I am going to prevent you from receiving any payment for 2 weeks on this capital. Well, I've sanctioned against approximately 800,000 in rewards that you would otherwise have received. So the operator, the stakers, everyone involved has faced a penalty of $800,000, but the principal, $1 billion, has never been compromised. And so this is a very important design to think about when you're building your AVS, because you can leverage large pools of capital without ever putting the underlying principal at risk. So you can build systems, for example, in the context of Lagrange, a prover network, that benefit from having a heterogeneous set of protocol participants running some of the most sophisticated hardware in the space with high amounts of stake, high costs. In the event that they don't perform under liveness SLAs, they can receive sanctions by the protocol that penalize them without ever hurting retail stakers, LRTs, anyone who is supplying them capital. They would only be sanctioned against the rewards they'd receive. And a lot of AVSs are going to come out, I think, initially with hopefully very cautious attempts to add slashing, because the risks to the overall ecosystem if someone does something incorrectly can be high if they provision too much capital and they have to sanction against it, and they can harm the principal. But Lagrange, and I think many of their teams in the space, I know Aethos is one of these teams as well, have thought very, very carefully about how can we take these systems that we have in production today that don't have slashing and move them into a world where slashing is now permissible. And moving into that world means in some cases you might need them, and in some cases you don't need slashing.
Yeah, adding to that, actually, that's very similar to how we've thought about it, so that's great. I don't think that's controversial at all. Because slashing conditions aren't possible on day one regardless, the way we approached it is you actually have a permission set of operators, so it almost operates a bit like a proof of authority model, even with economic security, and then from there, exactly, it's the idea that you miss out on rewards if you don't do something appropriate. And then the other part of how do you reduce kind of that risk of slashing is you want to have it that it's as deterministic as possible. The more subjective it is, the more likely that you start having complexity. But if it's highly deterministic, in our case, the actual way of implementing a policy should be you're specifying very, very specifically what the rules are, what information sources you're using, whether that's historical on-chain information or off-chain information. And so in that case, the slashing it should be minimized because you're not having to there's no subjectivity there. But even then, we've been thinking a lot about whether slashing is needed right as soon as it comes live, because you actually may not need it to start, and there may not be a ton of, it's not necessary.
Yeah, agreed. I think this is a good framework for thinking about rewarding liveness and penalizing safety violations. In the case of Hyperlane, this validator system that I described previously has been in production without slashing for a couple of years now, and we have hundreds of millions of dollars moving across that system. And so I think there's empirical evidence that slashing is not always necessary, but the benefits of slashing, I think, are twofold. So one is at the application layer, without slashing, in my opinion, it's more difficult to reason about risk exposure discretely, which basically means you can't use this kind of cost of corruption, profit from corruption model to reason about risk. And so it's hard to decide, what actions within your application can take on this kind of can take on the safety properties of a system without slashing. And so in our case, let's say you have a DAO that wants to do some sort of cross-chain governance action, which might care very little about latency or liveness, and really just wants to prioritize safety, because this is like the most important thing that their protocol does. You would want to know, can this validator set just lie about the action that my DAO is taking, and kind of rug this whole chain that my protocol's on? Maybe like there's tons of TVL on it. So I think slashing functions as a discrete function, basically, that allows applications to reason about risk exposure. And then for users, which I think we were alluding to earlier, it introduces a kind of accountability or insurance policy. And this is especially relevant in bridging, where I think the hack, the loss of funds basically dominates the kind of hack leaderboards in terms of the billions of dollars that have been lost and just kind of vaporized, rather than there being some sort of accountability policy. And in the case of a project like Wormhole, basically the backers of the project were able to backstop the user loss of funds. But I think having that confidence before using the protocol that is actually possible via some objective mechanism, rather than just like the investors have some sort of existing incentive for the project to remain secure, I think allows us to kind of build more robust and more discrete systems on top.
So kind of like touch back on the insurance portion a little bit. If we think about slashing, really is about like redistribution of the underlying kind of like stake capital, right? So I personally think of slashing as a way for us to implement a kind of like insurance system where, let's say, if a certain contract between, or a covenant between the service provider and the user has been broken, and this calls for a kind of like payout or a redistribution of assets, then that would be implemented in the form of slashing. And while I agree that, what's that called? The non-slashing model, where the withholding of rewards actually works as a sufficient disincentives, I do think that the whole situation is actually made a little bit more complicated if we have a shared pool. So this works very well if it's just a single pool. Like either I get the restaked value or I get the staked value, and then I mean the protocol alone can determine like I'm going to withhold the amount of rewards that I give to you, and my capital still remains the same. But if this amount of capital is shared among, say, 10 different AVSs, then the 10 AVS would have to agree, more or less, that we are not going to slash this, right?
No, I mean, look, if you're running infrastructure and you have capital provision for a single AVS or multiple AVSs, the cost of capital is the same. All that changes is the relative reward rate. And so you can still sanction against the reward rate, which is still a penalty on the principal,
Yes.
penalty on the rewards.
Yes, but so let's say if there's a slash in AVS B, and the amount of capital slash is like 50% of the total asset that operator has. Wouldn't AVS-A now have half of the shared security that it originally has?
That's the difference between attributable and pooled security. And it's also the difference between the rate with which is the amount of economic security that's configured to be slashable by each operator.
Yeah.
So those are parameters that are configured within Eigen, not by the AVSs.
I do agree with you. Yes.
Yeah. I see. And to add one more point, I just wanted to cover. So I think you made a very good point about comparing cost of corruption versus the amount that can be gained from corruption. And I think that framing is very, very important when looking at purely economic systems, because what you typically are trying to do is use a large pool of security to ensure against some malicious fault or some bad behavior. In the case of zero-knowledge systems like what Lagrange works on, one of the benefits is that we have the safety of our computation always guaranteed by proofs. So effectively, all we need is a one-of-n assumption on liveness for the provers, where the worst thing that you have is a delay in the proof being delivered, which can be sanctioned against by sanctioning against rewards. So I think this really highlights a very important point that the best way to get to a very secure AVS ecosystem is for builders, like a lot of the folks on stage, to be very deliberate over what the security imperatives are within their applications, and whether or not, maybe to your point, the security has to be slashable within design to ensure something, or to our point, it might not need to be.
Yeah, and the amount of economic security that's needed for what you're specifically doing. So $5 billion of economic security for one group is not the same as $5 billion for another AVS. You actually may not need, you likely do not need the same amounts across each group.
So I think fast forward a little bit, right? We have 8 minutes left, and let's talk about LRTs, right? This has already becoming a very prominent component, right, currently within the restaking ecosystems. Do you guys see any risks potentially associated with LRTs, or?
I can answer. You can go first, Nikhil.
Yeah, I mean, that's actually a big risk. That's actually a big risk vector that we think about from an AVS standpoint, right? So if all of your economic securities is coming from one LRT, that's probably not the position you want to be in, and so you want to have a diversified set. The other part there too is what specifically is the LRT doing on the back end for their token? That's something that as an AVS you have no control over, but if it's something that they're doing or they built out a side product that then results in a depeg, that's a huge challenge as well. The other one is, I know like Affine, I think they're giving a talk after this, is thinking a lot about kind of circuit breakers and risk management for their LRT. Those kinds of things are important to consider, but I actually see LRTs as like a sizable risk vector when you're thinking about economic security. So you have to assess each LRT, figure out how much economic security you have from each of those, rather than just saying we're just going to have one from for our entire security.
Yeah, so to caveat my point on this, Lagrange works with most of the major LRTs, as does I expect a lot of people on stage. And we have great relationships with them, and I think a lot of these teams are some of the sharpest people in the space. But there are inherent risks over concentration of capital when you are looking at your operator sets and your stakers. And one of the both good and bad things of LRTs is their capacity to provision a large amount of economic security very, very easily for AVSs, right? They can click a few buttons and you get 4 billion restaked into you because they have the capacity, because they have the operators, they have the infrastructure to quickly spin up new AVSs, and they have the security already within their systems. And so that's a fantastic way to be able to have an efficient ecosystem that can bootstrap economic security faster than ever before in crypto. But there are risks over capital concentration. One thing I do want to highlight from Nikhil's point, we should think of where the contract or the token risk sits with an LRT. If you have, for example, EasyETH or EETH that you're using as underlying collateral, you do face the risk of a depeg. But if you have native ETH that's provisioned from one of these LRTs, you don't face the risk of a depeg. Because if their token depegs and faces some issue based on having too high withdrawals and not being able to move off beacon, then the capital that you have restaked into you has not depegged, though. The Ethon beacon or the LSTs that were deposited still exist. They're still underlying your system. If you have a slashing condition, they're still slashable, and there's still an inherent cost of capital associated with them. The EasyEth or EETH token that might depeg or any of the other PuffETH, et cetera, that is an extrinsic risk that doesn't, in fact, affect most AVSs.
Yeah, I want to highlight maybe an interesting case study that Hyperlane's been working on with Renzo recently, which maybe reflects some sort of new paradigm, and as well as a new risk surface area for us to think about, which is basically Renzo wanted to offer their users the ability to get access to their EasyETH product on L2s because of the cost benefits to users. In order to do that, obviously, they need some interoperability mechanism, and they can do two things. So one, they can either basically manage liquidity across all these L2s and kind of basically have to actively manage balances across the native bridges, which, as we all know, have oftentimes long delays associated with them. Or they can basically have a kind of on-demand liquidity system where a user kind of requests to mint some EasyETH on one of these L2s and uses a protocol like Hyperlane to basically ensure that there is sufficient collateral on the L1 reserved for provisioning this liquidity, but that liquidity can basically be available to any of these on-demand L2 users. And in order to secure that interop system, they're actually leveraging a separate portion of their EasyETH as a stake delegation for the Hyperlane AVS. Now, obviously, we don't have slashing live yet within EigenLayer, but this represents an interesting synergy between an asset issuer, in this case Renzo, and their ability to actually secure that asset issuance across kind of, I guess, non-Ethereum mainnet chains. And they have to decide basically what their exposure is going to be for how much collateral they're going to reserve for securing this interop system and how much liquidity they want to reserve for this kind of on-demand product. But ultimately, the benefit of this model is the asset issuer, or in this case, Renzo, has the ability to express their own risk tolerances rather than some kind of global system-wide expression or I guess prescription. And I think what we should all strive to do as kind of designers of these AVSs is enable the operators and the applications who are taking on exposure to your AVS to have an interface that allows them to express their own kind of risk preferences, such that they can also, they're not just trusting your development team to assess their risk exposure, basically.
I regret that we don't have 4 more hours to talk about this. I mean, this panel is only for 45 minutes, and we haven't got a chance to talk about risks involved with dual staking, involved with operators, right? Risks involved with, say, our node client softwares, right? So all of those things we haven't got a chance yet. But right now, I'm gonna open the floor and see if anyone has any questions for our speakers.
Come on, there's got to be somebody. Did we really bore you?
I have a question.
Please.
So when we talk about LRTs, we talk about like depegging and stuff like that, right? But I would like to kind of like ask this question: like, would say the OPSEC of the projects that is actually issuing all these LRTs, does it actually kind of like factor into the entire risk equation?
Oh, yes. Without a doubt, the operator selection that these LRTs use is one of the most important factors for underwriting your relationship with them. And that's a phenomenal point. And I think when developing an AVS across the board, you should always look at what is your operator concentration, who are these operators, what other software do they run, and what track record do they have for performance. And the best LRTs, surprise, surprise, work with the best operators. And the best operators work with the best AVSs. And so you can look and you can start seeing pockets within the ecosystem converge around where there is high security posture. And there are applications, there are developers, and there's an ecosystem of projects that prioritize keeping user assets safe and keeping the overall slashing risk to a minimum. It's a phenomenal question. Operators are one of the most important things in the equation.
Yes.
All right. No question from the audience? Oh, okay, please.
So, there should be no surprise. Lagrange builds an EigenLayer, but we have a tremendous amount of respect for every builder in the space building anything that they put their heart and soul into bringing to market. One of the things I'd say, just as a macro point that I find troubling right now, is there are a lot of attempts to try to source new types of capital for restaking without answering the core question of what are we going to build on top of this that can efficiently pay yield into this capital. If we move from 16 billion to 50 billion to 100 billion in staked or restaked assets that are available for AVSs or AVS equivalent software, I mean, all we do is kick the can down the road of how do we actually pay yield on this? How do we pay 50 basis points on 40, 50 billion dollars? And so I would really suggest that people in the space think carefully, not about how do we support more assets that we can restake, but how can we develop systems that can leverage this restaked capital to its fullest and actually be able to pay enough yield to keep it within the systems? Otherwise, the whole ecosystem becomes a point farm. Yes, the AVSs right now, I would say, is the limiting factor in being able to expand the ecosystem, not the need for more types of capital we can support.
Right, you're basically looking at us to be able to generate all the yield right now. Us and like a few other AVSs that are live. And hopefully there'll be more.
I think just to comment specifically on maybe some of the architectural trade-offs between Symbiotic and EigenLayer, I think one thing that is maybe interesting in terms of the diverging approaches is Symbiotic's basically enshrinement of these managed vaults, which essentially look like similar to the LRTs, but within the staking interface. And so stakers, instead of choosing an operator and kind of taking on whatever risks the operator is exposing themselves to, they can opt into one of these managed vaults, which could potentially kind of abstract over many LRTs or many operator sets, as well as potentially even have some rainy day DeFi activity or something. And so I think what the trend that I see is basically there will be kind of more and more sophisticated structured products on top of these things, and Symbiotic is just kind of one step in that direction of introducing DeFi to LRTs, basically. But I think, yeah, in terms of the equilibrium that's reached, I agree that there probably needs to be kind of a balance on the demand side. I think it's cool that all these LRTs have such competitive incentives for figuring out what the best allocation of their restaked capital is. And that gives us kind of a high leverage point. So I think we're definitely the benefactors of more competition there. But yeah, it'll be interesting to see how things trend in terms of what DeFi products get built on top.
Okay, anything else? If not, we're going to close this. And thank you everyone for speaking.
Thank you all so much.